Hello everyone, welcome back to my YouTube channel. In this video, I want to explain how to solve the next three questions, which is question 4 until question number 6 from EJU Physics 2019 first session. You can check link on the description box below if you want to watch the solution for the other question on this paper, or check my EJU playlist for another paper. Okay. Let's start from question number 4. As shown in the figure below, one end of a lightweight inelastic string of length L is fixed in place at point O. This is our string and then this is point O. And then a small object P of mass capital M, this is object P of mass capital M, is attached to the other end. While keeping the string taut, P is raised to position A. P is raised to position A, which is the same height as O, and is gently released. And then P inelastically collides with small object Q of mass M. After we release P at point A, it will move towards this path and then it will collide inelastically with object Q. Object Q initially at rest at position B, directly below O on a horizontal floor with friction. After the collision, P rises to position C, whose height above the floor is L over 4. So after collision, object P will rise to position C, and then Q comes to rest at position D after sliding distance D on the floor. Let us denote mu prime as the coefficient of kinetic friction between Q and the floor. The question is, what is D? We want to find the distance traveled by object Q after it collides with object P. To find D, I need to know the velocity of object Q right after it collides with object P. So I need to find phi. And then after finding phi, I'm pretty sure we can find D. The question is how to find phi. Phi is the velocity or the speed of Q after collision. If we talk about collision, we can use conservation of momentum. Conservation of momentum states that the total momentum of a system is conserved in case the system are closed. So in the closed system, the total momentum must be conserved. So by finding the by using the conservation of momentum, I can say that the total momentum of object P and object Q before collision, momentum of P plus momentum of Q before collision must equals to momentum of P after collision plus momentum of Q after collision. This conservation of momentum is occur at position B because we see the moment before it collides and right after it collides, and then that moment is happen at point D. So this equation is at point B. Momentum of P at point B is the formula of momentum is mass times velocity, yeah. Since I focus on position B, then the velocity is velocity of object P at point B. Let I write it down as phi B. So mass of P times Vb plus mass of Q is m. Before it collides, Q is at rest. Since it is at rest, then the velocity of object Q before collision is equals to 0. Therefore, the momentum of Q is equals to 0. Is equals to momentum of object P after collision, right after collision at point B. The momentum of object P is mass of P times the velocity right after it collides at point B. Let I denote as Vb prime plus the momentum of Q right after the collision is mass times V, mv. Remember this one or this quantity that we need to know. So we focus to find this one. To find V, of course, we need to know Vb and Vb prime. Remember that Vb is the velocity of object P before it collides with Q at B. And then Vb prime is the speed of object P after it collides with Q at point B. To find Vb, we can use conservation of energy. If you focus on object P, initially object P is at position A, and then it will travel along this path, and then it will reach point B. By using conservation of energy, the total energy at point A must equals to total energy at point B. Total energy means the mechanical energy, ya. Mechanical energy is the sum of the kinetic energy and potential energy. So I can say that the potential energy plus kinetic energy at point A, PEA plus kinetic energy at point A must equals to PEB plus kinetic energy at point B. In this equation, we focus on object P. Since object P is gently released from position A, that means the initial speed of object P is equals to 0. Since the initial speed is equals to 0, that means the kinetic energy is equals to 0. Because the formula of kinetic energy is half mv square. If the speed is equals to 0, then the kinetic energy is equals to 0. I can cancel out this one. And then, since B is the lowest position, then the height of object at position B is equals to 0. Since the height is equals to 0, that means the potential energy is equals to 0. Because the formula of potential energy is mgh. If the height is equals to 0, then potential energy is equals to 0. Okay, potential energy at point A is mass times g times height. The height of object at point A is equals to the length of the string, which is L. The height is equals to the length of the string, yeah, which is L, is equals to half m Vb square. We need to find this quantity, and then I will substitute it to our conservation of momentum. You can cancel out m here, and then you can cross multiply 2 to the other side. You will get 2gl is equals to Vb squared, then Vb is equals to square root of 2gl. I will substitute this into that expression. But before that, I want to find phi b prime. Remember that phi b prime represents the velocity of object P right after it collides with Q at point B. After it collides with object Q, object P moves with an initial speed phi b prime, and then it will rise until it reaches height L over 4. So by using the same concept, which is conservation of energy, we can find phi b prime. But now we focus on position B and position C. So potential energy at point B plus kinetic energy at point B is equals to potential energy at C plus kinetic energy at point C. Remember that this equation is used after collision. After collision. So the kinetic energy of B is not the same as KEB in this part. It is not the same. The first one is before collision, and then this one is after collision. So these two things are different. Okay? Potential energy at point B, since B is the lowest position, then the potential energy is equals to 0 because the height is equals to 0. And then kinetic energy at point C is also equals to 0 because this is the highest position. That means the speed of the object at this position is equals to 0. Since the speed is equals to 0, then the kinetic energy is equals to 0. Kinetic energy at point B after collision is equals to half m phi b prime square is equals to potential energy at point C is equals to mg times L over 4. The height of the object is L over 4. mgl over 4. We can cancel out mass, and then I can cross multiply 2 to the other side. Then I will get phi b prime being squared is equals to gl over 2, and then phi b prime is equals to square root of gl over square root of 2. I already get phi b and phi b prime. The next step is I will substitute it into our conservation of momentum to find phi. Don't forget, yeah, we want to find this one. Okay, if I substitute it, I will get m times phi b, which is this one. I can write it down as square root of 2 times square root of gl is equals to m times phi b prime, which is square root of gl over square root of 2, plus m times v. And then let us isolate this v by first moving this into the other side. Then I will get m square root of 2 square root of gl minus m square root of gl over square root of 2 is equals to mv. Of course, we can vectorize m square root of gl. Then I will get square root of 2 minus 1 over square root of 2. 1 over square root of 2 equals to mv. And then if you express this into single fraction, we will get m square root of GL 2 minus 1 over square root of 2 equals to mv, and then I will divide this small m to the other side to obtain v equals to m square root of GL over m times 2 minus 1 is 1 times 1 over square root of 2. This is our v. This is the speed of object Q right after it collides with object P. And then, after we know the speed of object Q, we can find D by using the formula work done is equals to change in energy. Work done is equals to change in energy. As you can see, for object Q, initially object Q has an initial speed which is equals to this. This is the initial speed of object Q, and then the final speed of object Q is equals to 0. That means the kinetic energy of object Q is taken out from this object. The kinetic energy is being used by work done due to friction. So work done due to friction is equals to the change of kinetic energy. Of course, there is no change in potential energy because object Q moves horizontally. There is no change in height. So the change in energy here refers to the change of kinetic energy. And then the work done here refers to work done due to frictional force. If I draw frictional force in this diagram, frictional force is directed to the left because the object moved to the right. The formula of work done is force times distance, but since the force is in the opposite direction of distance, then work done due to friction is equals to negative F times D is equals to the change in kinetic energy means kinetic energy at final position, which is D, minus kinetic energy at initial position, which is B. Of course, kinetic energy at D is equals to 0 because the object is at rest at position D. That means the speed of the object is equals to 0, then the kinetic energy is also equals to 0. And then I can cancel out the negative sign here as well. Then my equation is Fd is equals to half m, the m is small m because we focus on object Q now, times v square. As you remember, F frictional force is equals to the coefficient of frictional force times normal. Normal contact force is going up and the weight of object is going down. These two forces must be balanced. So the normal contact force must equals to mg in this case. So the normal contact force here is equals to mg. By substituting F by mu prime mg times D is equals to half m v square. V is this one. I will get, don't forget to square it up, yeah, v square, so we have to square it up. I will get m square GL over m times 2. M square, oh, don't forget this also have square. And then if you simplify it, you can cancel out this small m here. and then I will get mu prime mgd is equals to m square gl over 4m, and then move all of these things to the other side, then I will get d. So our d is equals to m square gl over 4m square mu g. Cancel out g, then my final answer is d is equals to m square l over 4m square mu prime. So our final answer for question number 4 is number 1. M square L over 4 mu prime M square. The question is number 1. Okay, that's it for question number 4. Let's proceed to question number 5. For question number 5, we have a vertical spring pendulum. So I have spring pendulum is formed by suspending a small ball of a certain mass from a lightweight helical spring. So we hang a small ball into a spring. When the ball is at rest, the position of equilibrium, when the ball is at rest at the position of equilibrium, the spring is stretched distance d from its natural length. The period of simple harmonic oscillation of the vertical spring pendulum is t. Next, the same ball is attached to one end of a lightweight inelastic string of length L, and the other end is fixed in place. So we have another arrangement, yeah. When this is made to undergo oscillation with small amplitude in a vertical plane of as a simple pendulum, it has the same period. So for our another arrangement, it has the same period. The question is, what is L over D? L is the length of the inelastic string in our second arrangement, and then D is the stretch distance from our first arrangement. If you remember the formula of period of a simple pendulum, so I talked about the second arrangement first. For a simple pendulum, you have to imagine the second arrangement. We have a simple pendulum. For a second arrangement, which is simple pendulum, the formula of period of a simple pendulum is T equals to 2 pi square root of L over G. This is the formula of period of a simple pendulum. 2 pi square root L over G. L is the length of the pendulum. This one. For our first arrangement, we have a spring pendulum. We have a spring pendulum. For a spring pendulum, the formula to calculate its period is T equals to 2 pi square root M over K. This is the formula to calculate the period of a spring. Period of a spring. M is the mass of the object, and then K is the spring constant. If I want to find L over D, of course, I need to know where can we find D in these two, where can I find D from this equation? D is the stretch distance of the spring. If we talk about spring, I have formula force equals to K times extension. This is the formula that we can use for a spring. F is force, K is the spring constant, and then X is the extension. In this case, the force is produced by the mass. Our force is produced by the mass. So F here can be substituted by using weight of the mass, which is M times G, equals to K times X. X is D. Our extension is D in this case. So K times D. Then K is equals to mg over d. So I will substitute this into our equation. Then I will get t equals to 2 pi square root m over k, which is mg over d. Of course, we can cancel out m here. Then I will get 2 pi square root 1 over g over d. 1 over g over d. If we express it in a single fraction, I will get d over g. And then last but not least, since the period is the same, we can compare these two equations. So 2 pi over a square root d over g must equals to 2 pi square root L over G. Square root L over G. Of course, we can cancel out 2 pi here, and then I can square both sides to obtain d over g equals to L over G, and then we can cancel out g. Then we will obtain L to G is equals to 1. So my final answer for this question is number 4. Okay, this is for question number 5. Let's proceed to the last question in this video, which is question number 6. Let us denote as r the radius of the Earth. So r is the radius of the Earth, and g the magnitude of acceleration due to gravity at the Earth's surface. So r is the radius of the Earth, and then g is the acceleration due to gravity at the surface of the Earth. As shown in the figure below, an artificial satellite is moving in uniform circular motion, concentric with the Earth, with radius 2r. So I have an artificial satellite which is moving at a distance 2r from the center of the Earth. And then the question is, what is the period of the satellite's uniform circular motion? We want to find the period of the satellite circular motion. Since the satellite moves in circular motion, of course we can use circular motion equation, which is centripetal force. Centripetal force is equals to mv square over r. mv square over r. First of all, let I denote mass of the artificial satellite as m. So the mass of this satellite is m, and then mass of the Earth is capital M. Capital M is the mass of the Earth. And then, since we want to find the period, we can combine this equation with this one. V equals to omega times R. Omega is the angular frequency. So, Fc centripetal force is equals to m omega square R square over R. We can cancel out R here. And then to find the period, we use equation omega is equals to 2 pi over period. So, centripetal force is equals to m times omega square, which is 4 pi square over t square times R. This is the equation that we use to solve the question. Centripetal force is provided by the gravitational force between the satellite and the Earth. The formula of gravitational force is gm1m2 over r square. So the centripetal force is provided by this one. So I can substitute centripetal force into gm1m2 over r square. So I will get gm1m2 over r square is equals to m times 4 pi square over t square times r. Remember that r is the distance from the object and the center of the Earth. R, this small r, is the distance between object and center of the Earth. By simplifying this equation, I will get cancel out m here, and then I think I will cross multiply it first, yeah. I will get cross multiply t square to the left hand side. I will get gm t square is equals to r square to the other side, 4 pi square r cube. Remember, we want to find period. Period is t. So t square is equals to 4 pi square over gm r cube. By the way, this is the Kepler's third law. Kepler third law. Okay, let us change r here into 2r. Then I will get t square is equals to 4 pi square over gm 2r cube. Then I will get t square is equals to 4 pi square over gm times 8r cube. And then square root of this expression is equals to period. But if you see from the possible answer here, we need to express it in terms of g. G is the acceleration due to gravity at the Earth's surface. Acceleration due to gravity, or G, can be calculated by using equation gm over r square. This is the gravitational field strength. This r is the distance at the Earth's surface, because they already tells us g is the magnitude of acceleration due to gravity at the Earth's surface. So in this equation, r represents the distance from the center of the Earth to the Earth's surface. So g is equals to gm over r squared. So gm over r squared can be substituted by using small g. Okay, yeah, let's see from this equation first. I got t square is equals to 4 times 8 equals to 32 pi square r cube over gm. I think I will cross multiply r square to the other side, so I will get gr square equals to gm. Then I will substitute gm to our expression. Gm is gr square. T square is equals to 32 pi square r cube over gr square. Cancel out r square here, then I will get t. Square root of 32 pi r over g. Square root of pi square, yeah, pi square. Pi square here. If you simplify it, you will get pi times 4 square root of 2r over g. So my final answer is 4 pi square root 2r over g. Then our final answer is number 6. Okay, this is the end of this video. I really hope you guys can understand my explanation, and I see you guys on my next video. Thank you and bye-bye.